Good morning, everybody. And while we continue with our series of seminars in the lab, and again with some technical problems that I hope it's already solved, and we move. It's a little bit surprising that after we always have problems. So, and I'm really very happy to have Kasia talking for us today. So thank you very much, Kasia. We were considering that maybe you can come to visit and do the seminar in person, and still I hope you can visit in the next month. So this is just, but that's perfect. And Kasia is talking about a topic that is very interesting and very interesting for us as well. It's two-photon vision. And I asked, in the spirit of these seminars, I wanted to have a very type of tutorial type, so we can learn. So I'm sure that this is what you are basically preparing. We have around well, kind of flexibility, but around 40 minutes, something like this, if that's okay. And then later we can have any questions or comments. So thank you very much, and please, floor is yours. Oh, okay. Sorry, I forget your introduction, because you are already we already know you from our collaboration and everything. So I think just in the interest of time, go ahead, Kasia.
Okay, thank you very much for inviting me. I'm very honored to have this seminar, and I hope maybe in the summer we will talk about this visit. And two-photon vision is quite new, and I would say a very elite subject. Therefore, I'm very pleased to have this seminar and share our results. The title is Two-Photon Vision, the Mechanism, Characteristics and Applications, and it is connected with the title of my grant, which was finished this year. So I will just present main results, and it will be some selected experiments, not everyone that were done here in Poland. But I would like to highlight the difference between one and two-photon vision in this seminar. So this is the outline. At the beginning, I will tell about the physical mechanism of two-photon vision. Then I will move to our latest results on spectral sensitivity of two-photon vision. And then I will focus on currently main application, which is two-photon perimetry. And at the end, I will tell about measurements of pupil light reflex caused by two-photon stimulus. So in 2014, we published a paper in PNAS about perception of pulsed near-infrared laser beams. These beams were perceived as having color of half of the applied wavelength. So it means that, for example, 1000 nanometer was perceived as 500, so it was green. And for example, 1100 was perceived as 580, so it was like yellow. So we showed that all of our participants, it was 30 people, were able to match the color, and that perceived color was similar to half of the applied wavelength. But we also showed what is the mechanism of this process. So let's visualize what happens when such pulsed laser beam hits the retina. The intensity in space and time is not constant because we've got pulsed laser. However, in this simple picture, the pulse width and frequency are not to scale. So to better image what happens, we just focus on the laser that we start with 200 femtosecond pulses and 76 megahertz. And when we calculate it, it means that separation in time between pulses is 13 nanoseconds. And after recalculating it for the space separation in vacuum, we obtain almost 4 meters separation between the pulses, which occupying only 60 micrometers in space. So it shows that almost every photons are delivered into the retina in such a very small time, and between that time is very long delay to the next part of the photons. And we measured average power, mean power, with our power meters. So we just do not know about this high intense of the photons flux, which is very short and very separated one between the others. So during such short laser pulses, photon fluxes are extremely high, and then it can happen that absorption of 2 photons instead of 1 of twice higher energy is possible. And then this absorption occurs in our visual chromophores. So our visual chromophores isomerize because of absorption of 2 photons instead of 1 in the process which is called 2-photon absorption. But what is important, there is no fluorescence emission of visible light. Our visual chromophores isomerize, and the number of such isomerized visual chromophores is sufficiently high to cause perception of light. So in 2-photon vision, we've got something like cheating our visual system. Our visual system thinks that is perceiving visible light, so photons of twice higher energy. In fact, it is stimulated by photons of twice lower energy. So this extension of visible range of electromagnetic radiation requires further characterization, of course. It will be interesting to check, do all the features of light perception just replicate in longer wavelengths? And are there any difference between normal and 2-photon vision, which may indicate the clinical and practical and other usefulness of this phenomenon in our normal life? So the data I will present were obtained with the use of several optical systems. In Poland, I work in 2 places, in Nicolaus Copernicus University in Toruń, and then I've got this system which is constantly changed and enhanced. And in Toruń, I cooperate with Agnieszka Zielińska. Another system was designed in Gdynia and then moved to International Center for Translational Eye Research in Warsaw, which is the 2nd place of my employment. And then Marcin Marzejon is my main colleague which is working there. So both of these students are very talented and actually at the final stage of their doctorate. And also there are 2 other systems which were constructed with the help of AM2M, which is spin-off company in Toruń. And first was moved to firstly to the Cleveland, to the laboratory of Chris Palczewski, and now it is placed in Irvine because Palczewski moved to Irvine. And in Cleveland, with this system worked Daniel Rumiński, who was postdoc there, and many interesting results were obtained there by Daniel. And also there is another system which is placed in a real ophthalmology clinic in Heidelberg University in Germany. And then with this system worked Grzegorz Łabus, who provides very interesting clinical results about 2-photon perimetry or microperimetry with ophthalmic patients. So to move to the data. So it is nothing special that light above visible range, so-called visible range, is perceived, because the perception of light depends on light intensity. So it means that even in 1947, it was measured that when we just use very intense light, we can perceive it up to 1000 nanometers. And this the threshold of perception is of course higher. It is 9.5 orders of magnitude higher than for maximum of foveal sensitivity, which is at 560. And when we applied our laser system from Toruń, for example, which is optical parametric oscillator with pulses of 200 femtosecond and 76 megahertz frequency, and we measure absolute visual threshold for that laser from 750 to 950, we see that the absolute thresholds points fit very well this curve, this old curve of visual sensitivity in near infrared. However, when we are using this pulse laser, we could also see which higher powers than at the threshold, that we could perceive another color, not red. It is like blue, and you know that very, very well because you did similar experiments. So the color was blue, white, maybe violet. And we also could measure the visual thresholds of disappearing this additional color, short wavelength color. And when we plot these thresholds on the same graph, we see that the sensitivity increases with wavelength in this range, and at some point it just intersects the one photon sensitivity. And for the longer wavelengths above that intersection point, there is only one kind of perception, and these wavelengths were perceived only with the short color. So now the absolute threshold, absolute visibility threshold is 2-photon threshold. And OPO system is very well, but there is some problems with obtaining the wavelength in this range, because this is fundamental wavelength of OPO pump. So here is the end of the signal beam, and here is the beginning of the idler beam, and there is no physical possibility to obtain the wavelength from that range and from that range. So it means, and this is very interesting range, as you can see, because it is close to maximum. So we decide to repeat the experiment with another laser source, which was actually especially designed for this purpose by our colleagues from Wrocław, Grzegorz Soboń and Dorota Stachowiak, and they designed the laser tunable fiber laser, which were used also for the same measurements, but in Warsaw. And with this laser, with a little bit longer pulse and a little bit shorter frequency, but it also results in some difference in thresholds, but we correct for that. So as you can see, these points also coincide with the points from Toruń, and we could see that also there is some region of this two-color perception, and absolute threshold follows the Wald curve, and also the another threshold, the other points fit well this 2-photon vision. And here we tried to compare the obtained shape with something that we know. So we measured these thresholds in the scotopic conditions. We were dark adapted. So we just thought that we could took a dark adapted scotopic sensitivity curve, multiply it by 2, because we've got in twice longer wavelengths, then divided it by eye transmission in the visible region and multiplied by eye transmission in the near region, and try to find if it fits to our results. And as you may see, in the shorter wavelength, maybe yes, but in longer, not very good. It is not very good fitted to our results in the longer wavelengths. So we've got also another curve which takes into account cone sensitivity, and this is photopic sensitivity, and we performed the same operations. So we multiplied wavelength by 2, divided by eye transmission in the visible region and multiplied by eye transmission in the near infrared region. And we obtain such very nice curve, which is, I think it is very close to our results. So, and of course, all of these measurements were obtained with the, for example, safe conditions. So this is our safety limits. So as you can see here, we can obtain 2 photon stars with different kind of colors, because it was perceived as blue, it was green, it was yellow, and it was orange and red. So we've got all colors, and 2 photon perception of laser. And these results have been presented on this year on ARVO by Marcin Marzejon. He has poster, and you still can see that poster because it is still available to the end of June. And also a part of these results have been published in paper in BOE in this year paper. This paper is mainly devoted to this laser, which was especially designed for us, but also there are some exemplary results, some points from this curve. Okay, to conclude this. This absolute threshold, which is connected with perception of red color, fit very well classical data for 1 photon vision. And the visual thresholds for 2 photon vision have been measured in the broad range from 800 to 1030 nanometer. And these thresholds were connected with the perception of color, which is close to half of the wavelength of the stimulating laser. And in the shorter part of this range, there is an overlap between these 2 mechanisms. Stimuli of higher intensities were perceived with 2 photon vision, but the absolute threshold was due to the 1 photon vision mechanism. And the maximum photon sensitivity lay between 1050 and 1100 nanometers and is rather flat. So it is good to know that it is probably no matter which kind of wavelength you can use here. And overall shape of the sensitivity curve resembles the photopic luminosity curve, which with wavelength multiplied by 2 and corrected by eye transmission, which confirms more conish character of 2 photon vision. And I will also go to this conclusion in the later part of my seminar. And maybe it is also worth to say that this intersection point of the 2 processes depends on 2 photon deficiency and 2 photon efficiency, and therefore it should depend on the duty cycle of the laser. So it allows for designing lasers which are dedicated to 2 photon vision applications in future. The second difference, because first difference is of course this spectral sensitivity, different wavelength, and the second difference between 2 photon and 1 photon vision is brightness of stimulus, which depends on the square of the intensity, not linearly on the intensity. And because intensity is connected with power, so the brightness of 2 photon stimulus depends on the square of power at the pupil. So how to show this? I can show you 2 experiments which show this effect. One was performed in Cleveland by Daniel. So the 1 and 2 photon visual thresholds were measured on the same background, but the backgrounds increases. So these thresholds were measured on dark background, and these thresholds were measured on light background. Yeah, the lightest was 1.8 times 1000 Roland, and it was done for 3 healthy volunteers. So each point represents thresholds measured on different background of particular intensity. And when we plot this on this log-log scale and feed the line, we found that slope of this line is very close to 2, which confirm this nonlinear character of 2 photon vision. And we also perform another experiment here in Toruń, which also shows almost the same, but not exactly. So it was not measuring the threshold, but we were trying to match the brightness of two stimulus. So subjects saw two stimulus at the same time, and the two photon stimulus was of particular intensity, and the task of the subject was to match the intensity of visible stimulus for that. And it was not very easy task, because the color of this two photon and one photon stimulus were not exactly the same. Especially for the higher intensity, some of the subjects, me as well, for example, could say that two photon stimulus is more yellow than one photon stimulus. So it is not easy to exactly say which intensity is exactly the same when you've got a little bit different color. Also for the lowest intense visible stimulus it was also impression that one photon stimulus was more blue than green. And for two photon, it was no any blue addition or bluish behavior for the lowest intensity. So for that experiment, the slope was 1.7, not exactly 2, and I think it was mostly connected with this difference of color. But of course, you cannot say that 1.7 plus minus 0.1 is 1. So it also shows that character of the perception of two photon stimulus is nonlinear. So is it useful for anything, this quadratic dependence? Yes, it could be useful. It could be useful because it changes the shape of psychometric function. So psychometric function is the function we describe probability of perception of any stimulus in the VS intensity of the stimulus in the log scale. So, for example, our visual system behaves like that when we just show subject very low intense stimulus. It is probability of seeing that is almost zero and almost zero. And when we increase the intensity, the probability of perception increases, and then it approaches almost 100%. And the shape of this curve, it is something that we would like to measure or to simulate in the visual threshold finding, yes, because visual threshold is defined as the particular level of the probability of perception of stimulus. Yeah, for example, we can use 50, 100% of perception. It would be our threshold. So we should know the shape of this function. And the shape of this function is modeled by the mathematical equations, and there are several parameters which are connected with the shape. For example, guess and lapse rate, which are connected with this behavior at the lower and higher end of this function. And also, which is most important for us, there is also parameter sigma, which is connected with the spread of this function. Because this quadratic dependence of brightness of stimulus is connected with the spread of psychometric function for the two-photon vision process. And it was shown by Daniel Rumiński in 2019 in BOE that yes, it could be even showed and measured. He measured it for himself because it was very troublesome and not easy to perform experiment, but he showed that for visible beam, psychometric function was twice, the two-photon vision has twice narrower psychometric function than one-photon vision. Yes, two-photon vision is red and one-photon vision is black here. And it means that when you are finding visual threshold with two-photon vision, it is more accurate method to find. It is less, how to say, less, the spread of obtaining different answers for different intensities should be smaller. And it was also shown in this paper that when we just perform, we just repeated the visual threshold finding for visible beam and for infrared beam in the same system, we found that the repeatability of finding visual threshold for infrared beam is substantially better than for visible beam. And this is a real result that I'm still seeing, because we are also performing another experiments, and it is repeatable, that when you are looking for visual threshold with 2-photon vision, you could be more accurate and more and the experiment could be easier to repeat. So the main application that was studied so far for 2-photon vision was perimetry and microperimetry, which we probably know very well. This is method which is used mainly for glaucoma screening, but also for some brain diseases and also photoreceptor diseases in ophthalmology. So as I said before, the main place when the 2-photon microperimetry is done with ophthalmic patients is Heidelberg, and Grzegorz Łabuz is the person which is responsible for that, for obtaining results. Here I can show you only the one results from, it was the first from the first paper, which showed that there is some normal level of sensitivity for the healthy subjects, and the decline was with the age was not statistically significant, which was very nice. And also that patients with diseases showed a significant decrease of 2-photon sensitivity compared to healthy ones. And when you are interested with these results for the 2-photon perimetry and clinics, I can recommend you the papers of Grzegorz, which were published in the last 2 years. So let's focus again on this quadratic dependence on brightness of 2-photon stimuli. So when you look at this integral, you can image that we can design the pulse train of different pulses and different repetitions frequency to obtain the same or similar integration results. So it means that, for example, maybe we do not have to use very short laser pulses, which are also very not too easy to obtain, and the lasers are very expensive. We can just use longer pulses and shorter repetition frequencies. And we published the paper about usefulness of picosecond Fable laser, which has 20 megahertz repetition frequency and 12 picosecond pulse. And we compare the visual thresholds obtained for femtosecond laser, which has 200 femtosecond and 60 megahertz repetition frequency. And we performed the measurements for 16 subjects, but 15 results. We used similar strategy like in many conventional microperimeters. And we tested 25 retinal locations with these 2 lasers. Subjects were dark adapted and so on. And we obtained 2 maps. So this is the sensitivity map for femtosecond laser, and this is the sensitivity map for picosecond laser. And when we compare it, the difference, the difference in sensitivity was almost 6, 5.9 plus minus 2.8 decibels. And difference which was calculated on the basis of this integral that I showed you before was 5.6 decibels. So it was in very good agreement with difference. So difference between these 2 lasers were connected only with difference in pulse repetition rate and pulse width. So to sum up this, the 2-photon visual threshold depends on the parameters of pulse train of the stimulating laser, and increase the threshold caused by pulse elongation can be compensated by decreasing of repetition frequency, and picosecond lasers, which are convenient to use and relatively inexpensive, can be used for 2-photon perimetry. So if yes, we can also try to use it. So as you probably know, in Toruń there is no ophthalmology clinic in university, and in Warsaw, in IKTER also. So we just travel to Bydgoszcz, to the ophthalmology clinic, and I just put the system into my car and traveled there 3 times during, and one was during pandemic, because it was first measurements was in 2019 in September, then second part of measurements before cataract surgery was in January in 2012, and then we have planned to measure cataract patients after surgery 6 months after the treatment. So it was during pandemic. Yes, but it was possible, and I was very happy that many of patients come again. And we measure the sensitivity, the visual sensitivity of these people of before and after cataract surgery, with the use of this picosecond laser and visible laser before and after. So before, we've got 32 subjects measured with the mean age 72. It was very hard to work with such old subjects, as you may see here in the histogram, even almost 90. And we also examined them 6 months after intraocular lens implantations. Here you can see the kind of cataracts that they had. And the procedure was quite long, because we measured their refraction, applied the drops. Then we performed Maya exam with conventional microperimeters. Then we have to try them with PC monitor how to use our system and align their eye in our system, which was also very hard with such old persons and such not very ergonomic system like our laboratory one. And then we perform infrared exam and visible exam, both in scotopic conditions, because everything was in darkness. And here you can see the results. This is sensitivity difference for 2-photon vision and for 2-photon vision and for 1-photon vision, sorry, before and after surgery. And as you can see, in both methods, we've got improvement. So it is difference for visible sensitivity, but also there is difference for infrared sensitivity. However, these two differences are different, yeah. So it's not exactly the same. Also the results for 1 and 2 photon sensitivity were highly correlated. And we also measured their sensitivity by this conventional microperimetry, and there is also non-zero difference between these 2 visits. But the change measured by Maya was not correlated by the change measured by our system, nor with 1 photon, nor with 2 photon modality. So I think that the difference between these 2 systems were too large to reliably compare the results, because Maya uses a very broad wavelength range, because it is yellow, white-yellow stimulus, and it was also obtained in a different way. It was not like scanning lasers. and also, of course, there were some background because it uses SLO, and there is some background on the visual field, and our system was in completed darkness, so probably the rods are somehow engaged in our system, and in Maya probably to lesser extent. So there are many differences, and you cannot compare the sensitivity measured by these two. The nice thing is that although they had cataract, they do not have many fixation problems. So it is very important for us that fixation is good. And it was a little bit improved after the cataract surgery, but not significantly. So we can believe that they look when we thought they look. So our results were also with our system were also okay. But there is another factor that influence that changed after the surgery. It was refraction error, because they have removed their natural lens and implant the phakic, then another artificial lens, and of course the refraction error was corrected after the surgery. And when we look for the correlation with this change of refraction and sensitivity measured by Maya, it was not correlated. Change of refraction and sensitivity measured by our system, but this one photon with green beam, it was also not correlated. However, for the two photon vision, we've got significant correlation between this two photon sensitivity and change of refraction. It means that this change of refraction influenced our results significantly, and it was another factor than just removing the media, how to say, scattering lenses than to take into account. So cataract surgery affected more one photon than two photon sensitivity, as it was, as we thought it should be done, because we think that near infrared light should be less scattered and less absorbed by this lens, by this cataract lens than visible light. However, the refraction change caused by intraocular lens implantation also influenced the two photon sensitivity, and correction of hyperopia decreased the two photon sensitivity, and correction of myopia increased it. So I think that our results should be continued. Our experiment should be continued, because we need more objective control of refraction correction for this two photon vision. It is some problems with that, because when we use subjective opinion, because two photon stimulus is almost never out of focus. It is not like having out of focus, very blur view of the two photon stimulus. It is also always sharp, but when you are not in a best focal plane, it is like not so good visible. It is not so bright. And probably when we ask the subjects if he or she could see well the stimulus before and after, maybe it somehow affected our procedure to correct the refraction properly. And at the end, I would like to show you the last experiment with pupil light reflex. So this is somehow this is the reaction of pupil on light stimulus, and it is governed by our our brain and our nervous system. And for normal vision, it basically follows luminosity function. And what is the pupil light reflex for two photon vision? It was very very naive question, and we would like to just check what is the difference. And we designed experiment with 3 stimulus. One stimulus, it was 2 photon stimulus. It was some kind, it was look like spiral of 3.5 degree size. And the same kind of spiral was done with visible wavelength, 520 nanometers. And also we measured the reaction for the stimulus, which was performed by using LED, and it was completely filled circle of the same size as this spiral. And in this experiment, we performed this brightness matching. So we have to be sure that the visible stimulus was the same brightness as 2 photon stimulus for each subject. And when we perform that and we measure all the parameters, we found that reaction of pupil for infrared stimulus was sufficiently smaller than for 1 photon stimulus. And it was also confirmed by different kind of calculation. For example, minimum pupil diameter, latency time maybe was not very different, but mean constriction velocity was different, time of maximum constriction was different. So for the same brightness, visible perceived brightness of these two stimulus, the reaction of pupil was smaller for the 2 photon one. And we think that it might be caused by weaker stimulation of rods by 2 photon stimulus, and also maybe more negligible scattering in the eye media, because stimulation occurs only in the focal region. But this weaker stimulation of rods is also confirmed by another experiments, and several of them showed that cones are probably more susceptible for 2 photon stimulation than rods. So first, it was dark adaptation curves obtained by 2 photon and 1 photon stimulation, and we found that the difference between cone and rod part of this dark adaptation curve was lower for 2 photon stimulus. And also when we measure the maps for sensitivity maps for 1 and 2 photon stimulation, the difference between perifovea and fovea for the 1 photon was bigger than for 2 photon stimulus, and also the shape of this spectral curve was also, as you remember, different. So to sum up, the effect of 2 photon vision occurs for wavelengths in the range 800 to 1030 and 300 nanometers, and the 3 primary colors are possible to obtain. In addition to wavelength, we have an additional factor, the temporal parameters of the pulse train generated by the laser, which affects the perception of 2 photon stimuli. The quadratic dependence of brightness on power means that the visual threshold can be determined with better accuracy, so the 2 photon vision should be useful for microperimetry. And several facts attest that cones are more susceptible for 2 photon stimulation than rods. The shape of the dark adaptation curve, the shape of the spectral sensitivity, the smaller pupil response, and the smaller differences in sensitivity between fovea and perifovea center. And also, I do not show any results, but I tell you about that practically there are no out of focus 2 photon stimuli, and they are either clear or invisible. And this is something which can be very useful in another application than microperimetry. And I think it is very worth to say that and to think about that. It is augmented virtual reality. So I would like to acknowledge all the people that were engaged in the results that are presented and in discussions and in another help. And also my research was funded by National Science Center of Poland and also by Foundation of Polish Science and European Union, and also by the city of Gdynia. Thank you very much. I can't hear you.
They can. You can not.
Yes, now I hear you.
Okay. Okay. Thank you. Thank you very much, Kasia. It has been great. So congratulations for all this enormous amount of work. So many experiments, so many nice results. So that's really great. And what we are going to do is I have a couple of questions, and we start with possible questions here in the room, and then maybe we collect some questions from the audience in the case that you are there is some of that. But first, just very quick thing. All the results you presented about microperimetry, this was pupil perimetry or was a standard subjective perimetry?
It was not pupil perimetry, it was standard subjective perimetry. So subject found the threshold by pressing the button.
Okay.
So it was not a reaction of the pupil.
Okay, because in the last experiment you also have a pupil perimetry working, although the pupil response seems to be small, right?
Yes, pupil response is small, so it is not very convenient for pupil perimetry.
Okay, that was my question. Just a kind of curiosity, how you are thinking in this augmented reality application? How, because what do you have in mind?
Reality application. I do not understand what is the problem with the application, because microperimetry, two-photon microperimetry can be done easily with just you have to have lasers, I don't know, galvo scanners and so on, and computers and some program to govern the behavior of optical systems. So it is quite easy to do with the actual knowledge. And another application that I think for future is this augmented virtual reality. There are also some scanning systems with these goggles, and I think that maybe if in future, when the pulsed laser sources will be minimized, maybe we can also think about the such kind of application, yeah, because this thing with difference in perception of out of focus stimulation would be very beneficial for that application. Yeah, so it is it is something for the future.
Very good. So thank you very much. Open for the people in the audience, that real audience persons. Danny.
Hello, thank you for your talk. It's very interesting. Accounting that it is possible to achieve two-photon vision for wave ranges for pulse duration from nanosecond to femtosecond, and also for repetition rate from few kilohertz to megahertz. What are the most suitable condition for this two-photon vision in terms of pulse duration and repetition rate?
I think it depends on application. When you just need a very bright stimulus, you have to look for the lowest repetition frequency, and also, for example, lowest the pulse length. Yeah. Also, there is issue with this safety when you've got a higher repetition frequency, higher than 50 kilohertz, then you can assume that your according to ANSI, that your pulse train is like average CW laser, so it makes some maybe easier to be safe. Yeah. So it depends. If you would like to very bright stimulus, to I don't know, to project it on the background, so then you have to shortening your pulse and lowering the repetition frequency, or you maybe have some another application that needs I don't know, you have to match the another things. So yeah.
So there are no ideal conditions, so it depends on the application.
Yes, it depends. I showed that this integral, it gives you the intensity, the brightness, yeah. But you can obtain the same value of the integral by using different repetition frequencies and different pulse length. So, for example, when you go to nanoseconds, then you have to lower the repetition frequency, and you can also see that. But another question is if that would be safe.
And what happens with the thermal load that is applied to the retina during this laser irradiation? Because
Yes.
The accumulation of pulses in the irradiated area may produce some thermal damage on that. Yes,
but I think that ANSI norms can protect you against. Yeah, so when you are just using, so they gave some frames of safe region when you can go through and use the lasers. And for example, when you've got very long pulses, to obtain sufficiently bright stimulus, you have to lower the frequency, but then you can just go below the safety region. Yeah. So this is your frame.
And if possible, one last question. You showed that the sensitivity for picosecond laser is lower than for femtosecond.
Yeah.
That would mean that for nanosecond would be lower than for picosecond?
Probably, if you use almost the same repetition frequency. Yeah.
Is that related to the spectral bandwidth of the laser?
No, it's related only to time parameters of the laser pulses. Yeah. Of course, spectral bandwidth also took, but when you assume the same spectral bandwidth for all these lasers, the thing that I show was only connected with this time parameters of this pulse train.
Okay, thank you.
Anything else, Alba?
Yeah, this is a good question. Also related to the question that Pablo asked before about the augmented reality integration of this approach. So I know, I mean, there are these laser beam scanning, like super minimized ones that are already used in these devices. So I guess the difference would be the pulse laser. So do you think, I mean, I have no idea how developed this I mean, in this sense, but do you think in a short term we would have like many miniaturized pulse lasers to use?
I don't know. I think it may be connected with the speed of you know, of development of the field. Yeah. Because now there is no possibility of there is no such small lasers, but you know, 20 years ago there is no possibility of having a camera in the smartphone. Yeah, now we've got 4, 5, 6 camera in one smartphone, so there are no smartphones. So I think I think it's a matter of time. And how to applicate it. I thought that when we've got this scanning goggles, then, for example, you can scan with MEMS the mirror, because the goggles could be done from, for example, dichroic mirror, yeah. So the visible beam from the world outside can go through the glasses, and the near infrared beam for 2-photon vision can be reflected into the eye, yeah. And you can scan of this mirror with the laser to just draw something, some letters, some shapes on the scene, yeah. And for 2-photon vision, you have to know problems with the out of focus, as I said, things, and also pupil reaction is also smaller, so maybe it is also very convenient for that application, that your beam that do not affect the reaction of the pupil for the light outside. So maybe it is worth to dig into that direction.
Definitely. Yeah, thank you.
Thank you very much. Anything else? We have any comment, any question from the virtual audience so far? No. No? No. It seems to be everything is very clear, Kasia. So if not, well, thank you very much again. So this is really great for us, you know, that we are trying here to resume after all these a couple of years not doing much in this topic. We're trying to resume new experiments. So we will be in touch, because probably we can collaborate again and do something together. So this is really exciting. So thank you.
I'm very excited too.
Yes, you are here. So thank you. And yes, because we changed the structure of the room, so I don't know where I'm looking. So I think we are closing here, and we will be posting the talk, because just probably other people are joining, can have a look later. For some reason they cannot join. So thanks again, and thank you everybody here and in the virtually, and I hope we can meet soon when you are visiting, or we go to Poland.
Okay, thank you.
Okay, bye-bye.
See you. Bye.